Hello Level 3s and welcome back to 3.4 Atomic Structure and Bonding and Thermodynamics. This is lesson 15. It is your very last of this topic. So what are our learning objectives today? Our learning objectives are to describe what entropy is, to determine if the entropy of a system and surroundings will increase or decrease, and to describe why reactions are spontaneous in terms of both entropy and enthalpy. It is highly likely this will take 2 parts to this video. So first of all, from looking at this picture, what would you think entropy is? Normally I'd ask that to you as a class, but obviously I can't get a response. So if you kind of look here, we've got this sphere which is highly ordered, and then it says entropy increases, and you can see that it's massively disordered here. So entropy is in fact a measure of disorder. Okay, so the more disordered a system is, then the higher its entropy. So entropy in a nutshell simply means disorder. Okay, and what does that really mean? Well, it actually is talking about the distribution of available energy. Okay, so the more ways energy can be distributed, the higher the entropy, the higher the disorder. Now, all substances, doesn't matter whether it's atoms or molecules, experience disorder because particles are always moving, which we know. If particles are in the solid state, then they're vibrating kind of slowly next to each other. Or if they're in the gaseous state, they're moving like crazy. And so therefore, there'll be lots of movement. Okay, so when you think high movement, you want to be thinking high disorder, and that means high entropy. Now, the symbol for entropy is a capital S, and its units are joules per Kelvin per mole. Now, you don't actually need to know that. That's a university thing. You'll do that if you're going to continue with chemistry next year, so you don't need to worry. Down the bottom here is a really lovely picture which demonstrates entropy. This is a snowflake, which you can see a snowflake is a really highly ordered system. Like, look at that beautiful snowflake. And if we leave that to kind of melt, then they'll all move apart and it'll be highly disordered. So when we go from solid to gaseous state, highly disordered, and we're going to talk about that. So if we look at this picture here, we've got a solid sitting in a flask, highly ordered. If it's highly ordered, there's a small distribution of energy, a low entropy. When it becomes a liquid, a little bit more distribution of energy, an adequate amount of entropy. And as a gas, you can see a large distribution of energy. It's moving around like crazy, high entropy. So one factor we're going to be discussing shortly is that changes of state are a massive impact on entropy of a system. So here's just some examples to get your head in the right space about this. So if we had some gas particles that I put into a container, over time those gas particles would spread out and become more disordered. Okay? Everything tends pretty much towards a state of greater disorder. Okay? If we have 2 gases and they're mixed, so here's gas A and gas B, and if they're in 2 separate compartments to begin with, and then I take away that boundary, then over time then they'll mix, and they're not going to spontaneously move back into these separate compartments into a more ordered system, and that's because reactions tend towards a greater disorder. Okay, and so these gases are more disordered. So like if you have an example of, like, if you have bricks, for instance, and you just stood there tossing them one after the other, what is the likelihood that they would end up looking back like this? And the answer is really slim. Okay, it is possible they could end up like that, but because there are so many more different arrangements that the bricks could sit in or fall in, it tends towards a greater amount of disorder. Okay, life tends towards disorder. So like, for instance, if we had a cup of hot coffee and we just left it to sit, what would happen? And you all know the answer is the coffee would go cold. And why would it go cold? It's because the heat would transfer to the surroundings and move around. It would tend towards disorder. It moves out of the system. And if we had this Coke bottle that we open, what's going to happen to the gas? The gas is going to escape. And why? Because it's going to go from this ordered place to a more disordered space. It's going to escape around the room and occupy the space of the new container, which is the room. So everything tends towards greater disorder naturally. So spontaneity or spontaneous reactions, as you know from redox, spontaneous reactions are ones that occur without the need to kind of do work. Okay, so they will work without having to add energy. And when we say that, we're not talking about the activation in energy needed to start a reaction, because every reaction needs a certain amount of activation energy. We're talking just about extra added stuff. So what you might not realize, but the second law of thermodynamics is that spontaneous processes always occur with an increase of entropy to the universe. So what they're saying is that spontaneous reactions occur if there's an increase in entropy. And entropy plays a huge role in chemistry, and so that's why we're talking about it today. But when we're trying to decide whether something is spontaneous or not, we have to both consider enthalpy, which ends up being the entropy of surroundings. I'll teach you that shortly. And entropy, and that's talking about the entropy of a system. So we have to compare both entropy and enthalpy to determine if a reaction is spontaneous or not. So just so we can have a bit of an idea, when we talk about entropy of a system, we're actually always comparing the products to the reactants. And S is the symbol for entropy, and you're not doing these calculations this year. It's just good to get in your head that we're always trying to compare the entropy of the products with the entropy of the reactants. Now, if we look at this reaction here, this is water melting, solid to liquid, which has also got the name fusion, if we think back to the earlier section of thermodynamics. So we know that a solid is far more ordered than a liquid. So the liquid particles are moving more, and therefore they're more disordered. So if we were to take whatever the value might be, the entropy of the products, and subtract off the reactants, we get a positive entropy value. And it's not meaning positive like endothermic, it's just meaning positive that there is an increase in entropy in this system. And we know that because water particles move around more than solid particles, and if they're moving more, there's a higher distribution of energy and a higher amount of disorder. And this is the sort of thing that we're going to be looking at as we go through this topic. So you won't actually calculate S this year, so you won't have to do this and you won't have to use this, but you need to look at equations like this and determine whether entropy would go up or down. And when you look at an equation and assess whether the entropy has gone up or down, this is actually referring to the entropy of the system. And so that when they ask you in the exam what's happening to the entropy of the system, you look at the equation. And I'll explain now all the possible ways that we can change the entropy of a system. Okay, so the entropy of a system, team, there are 4 categories that can increase the entropy of a system. Now, I do apologize that some of this is cut off with the screen of the screencast, but I'll fill you in if there's stuff that's missing. The most important thing to look for when you look at an equation to determine whether the entropy of a system is going up or down is state change. We've already discussed it, but we're going to discuss it again. If you're going from solid to liquid, you're going from a highly ordered to a highly disordered state, so entropy goes up. If you're going from liquid to gas, gas particles are moving far more than liquid particles, therefore the disorder of the system increases. If you go from solid to gas, which is sublimation, gas particles move far more than solid particles, therefore there's greater disorder. If you're going from a solid to a liquid and dissolving it in water, particles dissolved in water are moving around constantly, so again, disorder increases. So in all of these 4 situations, the particles have got greater kinetic energy, are moving more, and therefore there's increased disorder and increased entropy. That there, if you could put that sentence together, then you get a merit for the question, for that part of the question, which is pretty crazy. So my suggestion to you is every time that you're talking about a state change, make sure you use the words kinetic energy, link it to moving more, link it to the word disorder, and then link it to entropy. So those are kind of the 4 points that you need to cover to get full marks. So particles would have a greater kinetic energy, therefore they move more, therefore there's more disorder and increased entropy. You absolutely have to have this word disorder in your answer to get full marks. You'll see me do loads of examples in the next video, so don't stress too much. You just need to understand at this point. Okay, so the second thing that we discuss when we're looking at entropy of the system is the number of particles, okay, the number of moles of particles. So if there are more moles of product than reactants, then there are more particles moving about, which means there are more ways to arrange themselves. So literally more particles means more chaos and disorder, and that means entropy increases. So that's the second thing. So these are quite easy, really. So the first is that we look at state. Okay, gases will be higher disorder than liquids, which will be higher than solids. Okay, and then we look at the number of particles. More moles means more disorder, more entropy or greater entropy. The third is an increase in temperature. So if we had no change to anything, but there was an increase in temperature, well, we know that increase in temperature increases the particle movement because they have greater kinetic energy, more disorder, more entropy. Nice and easy. The last one here, which you can only see part of, and I can't seem to be able to move the screen a little bit here. Oh, that's not intended. Is the volume of increased volume for gases. So if you increase the volume for a gas, the entropy will increase, and the reason why is because if you increase the volume, there are more places. Oh, I nearly had it. For which the particles can arrange themselves, and more disorder, higher entropy. This one doesn't really come up at all. I've never seen a question on it, but these top two come up all the time. So let's continue with some examples. Okay, so here's the first task. Does the entropy of the system increase or decrease? So in example 1, we're going from liquid ethanol to gaseous ethanol. So this would be an increase in entropy. Why? Because gases have greater kinetic energy, they move more, there'll be greater disorder and greater entropy. Hopefully that makes sense. So if you look at the second equation here, okay, all gases this time. So we can't use a state change to describe whether the entropy would go up or down. But what we can do is we can see that there are 4 moles, 3 plus 1, versus 2 moles. So we can actually see that there are actually less moles on the product side, which means the entropy of the system is decreasing. There are less particles, so less ways they can arrange themselves, less disorder, less entropy. So this would be a decrease in entropy. Let's look at the last situation. So this one here, you've got a liquid, okay, and a gas going to 2 gases. So the first one is that you've actually got, the first point to make would be, you've got a liquid and a gas on the reactant side to just gases on the product side. Liquids are more ordered than gases, so therefore there would be an increase in entropy because the gaseous particles can move around more, there's greater disorder. The second thing is that you've got 2 moles on your reactant side, 1 and 1, and 3 moles on your product side, 1 and 2 make 3. So you've actually got a second point to make here. You can actually say that there are actually more moles as well, increase in the number of moles. So if there are more particles on the product side, there are more ways they can arrange themselves and the entropy will go up. So there are actually 2 reasons that you can put here for why the entropy of this third reaction will go up. Now you need to practice at these, so when you look at the equation, you have to assess what things are going on to increase or decrease the entropy of the system. This is called entropy of the system. Now I've got another task here, okay, which I'd like you to complete. So I'd like you to pause the video and just think to yourself, would these go up or down? And I'll show you the answers. If you have any questions, please let me know them on Teams, but it's really important that you can do this, that you can look at an equation and determine whether entropy of the system will go up or down. So here are the answers. If you have any questions, please let me know. Okay team, I'm going to pause here and I'll come back to you in the next video to talk about entropy of the surroundings, and then we're going to link the two together and do some examples. You're doing really well.